Hello, everyone. First of all, I'd like to express my thanks to Professor Shang Mutli for giving me this opportunity to talk on the Ophiolite of Oman. Where we have two Ophiolite naps being abducted to Oman with two contrasting tectonic settings. As you see in the picture, this is the typical landscape of the Oman Ophiolite, where we can see the mantle sequence and the crustal sequence all over. Actually, in Oman, most cities and most villages are built either on the oceanic mantle or on the crustal mantle. First of all, just allow me to give short background on Ophiolite. Ophiolite is interpreted to be a thrust sheet of ancient oceanic lithosphere, which has been abducted over the continental crust in the course of orogeny. Now, the term Ophiolite refers to a distinctive rock assemblage containing mantle ultramafic rock, the peridotite, overlain by crustal section, mostly made of gabbros, layered or massive, sheeted dikes, basalt, lava flow, and all these are covered by a thin layer deep sea sediment, mostly regular in shape. Now, these assemblages of Ophiolite are typically resembles newly created oceanic crust and uppermost mantle near the mid-ocean, the present-day mid-ocean ridges. And Oman Ophiolite is typically a good example of the present-day oceanic lithosphere. Now, the origin of Ophiolite has been a topic of much debate, actually, and two main theories have been proposed. One of them is the mid-ocean ridge theory, which suggests that Ophiolite form as a result of seafloor spreading, by which new ocean crust is created at mid-ocean ridge, and then moves away from the ridge as the earth tectonic plates move apart. And the theory is supported by the presence of pilolava, pilobasalt sheeted dikes, which are characteristic feature of oceanic crust formed at mid-ocean ridge. On the other hand, we have the supra-subduction zone theory, which suggests that Ophiolite are fragments of continental crust that were separated from the mainland mass and sank to the ocean floor. It also suggests that Ophiolite were formed by a process known as subduction erosion, where the continental crust is scraped off and carried down the subduction zone and eventually exhumed. This theory proposed that the Ophiolite also were formed in different tectonic settings at the collision zone between two oceanic crusts. And the theory is supported by the presence of high pressure metamorphic zone, metamorphic soil, plutonic rocks, which are not typically found in oceanic crust formed at mid-ocean ridges. And petrologically, Ophiolites are classified in two types depending on the mantle section, where we have the peridotite classified into either donite, harzburgite, lirzolite, or whorlite. So most Ophiolite, which are lirzolitic in composition, are related to the mid-ocean ridges, while the harzburgite Ophiolite are related to the supra-subduction zone, and we can see different examples worldwide. And the Oman Ophiolite is lying here, where we have Kleinberg-scene bearing harzburgite, indicating more to arc thorithic tectonic setting. Now, through the time, Ophiolite was first known and described from the Alps in the early 20th centuries, and was later discovered from almost every organic belt on the earth. And we have three major impulses of Ophiolite through the history, from Phanerozoic to Cainozoic. So we have the main pulse occurred before 750 million years in the Phanerozoic, and then 450 million years in the Paleozoic, and 150 million years in the Mesozoic. So we have a gap of around 300 million years between each pulses. Interesting to see that the Ophiolite in the Paleozoic was mainly related to supra-subduction environment, while in the Mesozoic, we have three types of environment related to Ophiolite. We had the mid-ocean ridge Ophiolite, we have bloom-related ophiolite and supra-subduction zone ophiolite. And this raises the question why we don't have this one in the Paleozoic, why we don't have the or rarely found a mid-ocean ridge or blue type in that time. Now, to distinguish the geotechnic setting of an ophiolite, usually geologists and petrologists try to study the fertility of the rock complexes, type and size of the ore deposit, mostly chromatite, by looking at the ratio of mineral phases, the type of residual apatite, is it lherzolite or Habsburgite. We look at the magmatic differentiation of the rock, chemical composition of the ore bodies, and most importantly, the geochemical affinity of volcanic strokes like the below basalt, in order to tell which geotectonic setting the ophiolite being formed. So for the supra-subduction unrelated complexes, that's a mid-ocean ridge environment, actually, we have three types of subduction unrelated ophiolites. So we have the continental margin type, CM type, we have the mid-ocean ridge type, MOR type, and we have the blue related type, the B type. So these are subduction unrelated ophiolite. On the other hand, we have the subduction related complexes where we have a fore-arc spreading environment, island arc environment, and back arc spreading environment. And petrologists try to use either petrophysical study, structural study, or geochemical study to distinguish the environment of these ophiolite. At the same time, ophiolite are formed either on fast spreading ridges like the Pacific Ocean, and these ridges are characterized by gentle slope, and they lack prominent rift valley at the ridge crest. In comparison to slow spreading ridges, we have a steep flank, prominent rift valley. Beside, we have many transform folds which offset the ridges. So that was just background on ophiolite and the debate on the type of ophiolite. Now coming to Oman, Oman actually is lying in the northeastern part of the Arabian Plate, which is bounded by the Levant transform fault and the Oman transform fault. And in Oman, we have two ophiolite actually. As you can see, the largest one here in the northern part, this is called the northern Oman ophiolite. And we have three blocks of ophiolite in the eastern part of ophiolite. So this is called the eastern ophiolite. And this one is called the northern ophiolite. So geologically, they are known as the Samail Ophiolite. This is the northern ophiolite in the northern Oman Mountain. And we have the eastern ophiolite represented mostly by the larger block, which is in the Masirah Island. So because that we call it Masirah Ophiolite. Now the Samail Ophiolite is segregated into 13 blocks, so segmented. And these blocks are known by the northern massif block, central massif block, and the southern massif block. Now, for comparison, the Samail Ophiolite is the largest, best studied one, and represents the complete section, actually, of the typical ophiolite, where we have around 15-kilometer thick sequences of mantle sequence, mostly Habsburgite and Dunite, followed by the crustal sequence, where we have three different types of gabbros: layered gabbro, foliated gabbro, and isotropic gabbros. And between these gabbro and the mantle sequence, we have the MOR. The gabbros are covered by sheeted dikes. And then we have three types of volcanic pillow lava. The first one is called the V1. This is the famous geotime pillow lava with more chemical composition. And we have the V2 and V3, mostly they are of calc-alkaline composition. In comparison to Masirah, Masirah is very similar in rock types to Samail, but with much thinner sections. We have around 5-kilometer thick ophiolite in Masirah, and they contain the whole sequence except that we do not have calc-alkaline lava within the Masirah. Now, the Samail ophiolite abducted Oman before 80 million years in a southwest direction. The age of the Samail ophiolite of the magmatic rock is 94 to 96. In comparison to the Masirah Ophiolite, it's older, much older. The age of magmatic rock are going back to 150 million years. And the time span of the magmatism is between 84 to 150. So the time span is much larger than the Masirah, which is only 2 million years. Here we are speaking about 70 million years. The obduction age of the Masirah Ophiolite is 65. Although it's older than the Samail, but the obduction age is younger than the Samail Ophiolite. So I'll start characterizing the Samail Ophiolite. As I told you, we have 13 different segments. The well-studied one is the southern part. This is called the Wadi Tayin Massif, and the central part called Healthy Massif, and the northern part Visit Massif. So the length is around 600 kilometers long, and the width is 150 kilometers width. And it's one of the best study of Ophiolite worldwide because it gives us an excellent section, well-preserved rock all over. Just to give you some example, you can see the mantle sequence all over Oman, the layered gabbro, the sheeted dike, polylava, and these are very typical to the present-day oceanic lithosphere. These are just examples. This is the old city of Muscat. It's completely built on the mantle sequences. You can see the polylava all over in Wadi Oman, the sheeted dike, well preserved, completely Oman, and you can see the moho. So the moho is well preserved and can be seen all over wadis and mountains in Oman, separating the crustal sequence with the gabbro from the Harzburg dike. Anywhere as you drive through, you can see it, and even you can walk on the moho and touch the moho all over, and even by driving the car during the sunset, you can see the color of the crustal material and differentiate it from the upper mantle crust. And most importantly, you can see beautiful mantle diabir, large mantle diabir with fossilized melt channels within the diabir. And this is the most studied diabirs worldwide. You can find it only in Oman, such diabir actually. You can see also old volcanic island with exotic limestone, which is metamorphosed limestone now overlying volcanics, oceanic island volcanic. You can see the deep sea sediment all over side by side in Oman. Now the evolution of the Samail Ophiolite started actually in late Carboniferous to Permian, where we start having updoming and rifting, which led to the opening of the new Tethys and the position of the Hawasna deep sea sediment, which are mostly radiolar and shear. And in the middle Triassic to early Jurassic, we have the volcanic activity, which went along with the continental breakup. In late Cretaceous, oceanic crust was subducted and its sedimentary cover formed an accretion ridge, which is represented by melange and the Hawasna deep sea sediment. So that was the situation before 300 million years, where we have the Paleotethys and starting formation of the ridges. And after 40 million, that means at the age of 260, we start, or the new Tethys start to be formed. So if we go to a Wilson cycle, where we start with doming and then rifting, formation of proto-ocean, and then the Tethys ocean. So this is the situation actually before abduction. That was the mid-ocean ridge here. And here we have the Hawasna basin, where all deep sea and deep sea radiolar sheets start to be formed. We have the exotic and the seamount, where the marble in Oman being formed, and the whole sequences of the different sediment and volcanics being formed. So that was Oman here, and this is Iran, and this is the Tethys Ocean in between. And continue previously, that was the situation where we have the continental crust of in Oman, the continental margin, and we have the oceanic crust, and here we have starting of subduction oceanic crust, and here we have the back arc environment. And this is typically what we see here now in Oman. At the present time, we see the Ophiolite here covering the Batain Plain. This is the Gulf of Oman. And here we have a tectonic window representing the old Proterozoic rock presented by the Nakhl Mountain and the Al-Hajar Mountain. Most of these being eroded, and remains of the Ophiolite here above the continental shelf of Oman. So this is the real view here, where you see the Proterozoic autochthonous rock represented by Jabal Nakhl and Jabal Akhdar. And here we see the Samail Gap represented by the Samail Fault. Here we see the mantle sequence, the Moho, separating the mantle sequence from the crustal sequence. So all over Oman, you can see these sequences together. And here representing the Proterozoic and Paleozoic rock represented by Jabal Akhdar Mountain and Jabal Nakhl. This is called the super sequence A. This is an autochthonous. And we have another autochthonous series, the tertiary sequence. In between, we find the allochthonous series represented by the Ophiolite and the deep sea sediment called the Hawasna. So the tectonic setting for the Samail Ophiolite, there are actually two schools discussing the origin of the Samail Ophiolite. One of them is represented by the French group, stating that the Ophiolite was formed in mid-ocean ridges, it's fast spreading ridges. And as evidence, they take the continuous layered gabbro section over tens of kilometers in Oman. And this implies permanent magma chamber at the spreading axis. And as example, today, permanent magma chambers are only encountered in fast spreading ridges with a spreading rate of more than 5 centimeters per year. On the other hand, the group which support the supra-subduction zone, they depend on the geochemistry of the lava, pyritic lava with calc-alkaline affinity sequence. And due to that, they propose a back arc basin model for the Oman Ophiolite. And a possible site for the subduction zone is preserved and can be found in Oman in an area called Sihattat area or Sihattat Dome, east of Muscat, where there are high pressure eclogite and blue schist indicating subduction zone environment. So the first group made all their study depending on vitro and structural study. The French group, mainly by Francois Boudier, other Nicolas, and their student, they made a lot of structural analysis, and they proposed this New Tethyan median ocean ridge trench intersection plus intra-oceanic thrusting. Now, all their study, they studied in detail the mantle diapir in Oman. And within the mantle diapir, they studied the MOR transition zone, which is occurring between the mantle sequence and the crustal sequence. This mantle transition zone is usually composed of dunite and whorlite, which are either melt impregnated or dry. The thickness of this MOR transition zones is around 400 meters. It's very thick on the top, and it's usually in the top of the mantle diapir. This is the MOR transition zone. And it starts from zero thickness at right of the axis and extend over tens of kilometers transversely and thinning to less than 100 meters of axis. Now in Oman, we have 5 diapirs. All of them are around 5 to 10 kilometers in thickness. And they are well studied by the French group. And they studied one of the best diapirs called the Maqsad mantle diapir here. And they found several evidences for mid-ocean ridge environment, which include plunging lineation, thick MOR transition zone, fan and tent-shaped foliation as a continuous structure, radial flow, gabbro lineation parallel to the mantle lineation, shear sense reversal indicating activity profile, many chromite buds with a lot of dikes in the mantle section. So they take these evidences to support their theory on mid-ocean ridge by comparing these magma chamber or diapir with what's going on at the present time. So they compare the MOR transition zone, the mantle diapir, with fast spreading ridge and magma chamber shape. And for magma chamber shape, we have different type. One of them is the onion shape with a large roof inspired from continental chamber. or we have tent shape with a narrow roof and wide isle. And this is typically in Oman, and the other example is found in the East Pacific rise. Beside, we have the funnel-shaped chamber. Mostly, it's found in the East Pacific rise also. So this is an example of the Maqsad Diyabir, where we find fossilized mantle lenses with layered gabbro within the Diyabir. And here we can see it's around 400 meter thickness and extend for 10 kilometers. Here's another example of a mantle Diyabir, another mantle Diyabir. So we have 5 large mantle Diyabir, which can be seen only in Oman. So they consider that the mantle transition zone here, representing a physical and chemical relay collecting melt issued from the mountain and delivering it to magma chamber and burst mantle lenses. So most of their study and most of their group is taken from studying structural analysis of mantle Diyabir and MOR transition zone in Oman. On the other hand, the proto-arc model, by analyzing chemically different rock and different volcanics, they found that these rocks contain high thorium, niobium, plus hydra slab component, contaminated axial magmatism. So these are the main characteristics they found. And they conclude that this combination is incompatible with ridge models of mid-ocean ridge contamination. Beside that, the axial crust was immediately and continuously overlain by hydrous, phthalitic, and boulolitic lavas, which is very similar to proto-arc subduction initial setting, such as the Ozyponian Mariana 4R and Hunter Matthews subduction zone. And they built this model for the subduction. And here we have the proto-arc spreading ridges, where the different magma here, the geotime magma and lacile volcanics being through. So here we have the geotime, which is more by magma, and lacile and alli magma are mostly phthalitic to calc alkaline composition. Now, by concluding these two groups, actually, we came to the idea that there is an evidence of transition from spreading environment to subduction environment. So both are correct. There are evidence for spreading environment, and there are evidences for subduction environments, which indicate that we have some transition from spreading to subduction. As we can see by studying the volcanic rocks and dike in the crustal sections, we have 3 volcanics. The oldest one is the V1, we call it volcanic 1 or geotime lava. And the composition is mostly in MOR composition. V2, the composition is island artholite, tubulnite, and V3 is alkali basalt. So these 3 volcanics indicate that we have transitioned from MOR environment to a subduction environment. Beside that, we have many periodicites with basal rosolitic composition, highly refractory type, and silica-rich gabbronorite, dike, and pyroxenite are very common, which indicate that we have also some transition from MOR to subduction environment. Here are examples of these volcanic, actually. This is the geotime lava, where you can see the tube. Typically, it's similar to the tube of present-day ocean volcanism. And this one gave us a more chemical composition, followed by the V2, it's called the alli lava, giving us an island artholite, and the alli polonitic composition here. And at the end, we have the racile volcanoes, which give us alkaline composition. So by analyzing the chemistry of these volcanics, as well as the different rock type, all these indicate that the late magmatism was of supra-subduction zone environment, and the early magmatism was of mid-ocean ridge environment. So both are correct. And if we study the chemistry of the rock from the southern part, this is what this area here in the southern part of the Ophiolite, it's typically showing MOR environment, while the northern part, the chemistry of the spinel and chromite is indicating that we have a subduction zone environment. And this is just a numerical modeling of the subduction here done by Duritz et al. 2016, showing how the subduction being initiated. And this is actually the real situation here in Oman. This is the subduction zone where we have the high pressure dome and Sihatat dome area where we can see the eclogite in the Sifa area, high pressure eclogite indicating a pressure of around 25 kilobar. That means a depth of more 70 kilometer. We have the Oman Ophiolite here at the top. Below it, we find the deep sea sediment Hawasna, which are all abducted over the Precambrian platform, Arabian platform. This is the present day situation. So in regional scale geodynamic, that was the situation before 85 million years. We have the new Tethys Ocean, and we have the Samail Ophiolite abduction. And at 65 million years, the abduction of the Masirah Ophiolite started. And this is the situation before 30 million years, the new Tethys Ocean being consumed, and we start opening the Red Sea in the western part of Arabia. So that was the case of the Samail Ophiolite. Now the case for Masirah Ophiolite, as you can see, Masirah Ophiolite is mainly outcropping here in Masirah Island, as well as in the southern part in an area called Ras Madrah. This is the geology of Ras Madrah, where we can see the Ophiolite with the blue color and the melange with this brown color. So it's covering 3 areas in Masirah and the Batain area as well as the Ras Madrah area. So they are, the age of this Ophiolite is mostly Jurassic, actually. And it contains 2 sheets, 2 ophiolitic sheets, plus Ophiolite melange. The melange is only covering the eastern part. The width of this Ophiolite is 40 kilometers, and it extends 450 kilometers in extension from the southern part to the northern direction. And looking at Masirah Island, it consists actually of 2 nabe. One is called the Upper Masirah nabe in the northern part, where it shows only the crustal sequence, mostly gabbro and alkali volcanic rock, and pillow lava. It's covering the northern part of the island. The southern part, which is called the Lower Masirah nabe, include the mantle sequence plus few of the crustal sequences. And these are just few examples of the Ophiolite outcrop in Masirah, where you can see the pillow lava, mostly alkali pillow lava, more pillow lava. We can see the mantle sequence, the Harzburgite, plus a few of the gabbroic rock. Also here we can see the gabbroic rock. We can see the deep sea sediment. We can see also the volcanic and the sheeted dike in several parts of Masirah and other outcrop. Besides that, the Masirah contains also several outcrop of chromite, and that was one of the main aspects for mid-ocean ridge, presumed by Rawlinson that mid-ocean ridge Ophiolite contain no chromite body, but in the opposite, we find a lot of chromite bodies within this mid-ocean ridge Ophiolite in Masirah. This is the real situation now for the Ophiolite in the eastern part of Oman. This is the Masirah Island. This is the Masirah Graben, and this is the Masirah Basin, Owen Basin, and Owen Ridge. All these are covered by water, and the Masirah is just being abducted upward with a height of around 100 meters above the sea level. All these Ophiolites are covering the crystalline basement of Arabia, the Arabian continental margin here. And you can see that this Ophiolite is characterized by large number of faulting, either normal fault or thrust fault. So the evolution of this Masirah or Eastern Ophiolite, the Masirah Ophiolite is thought to have formed in a magma-poor environment because of its late Jurassic age, more type geochemistry, and the Ophiolite sequence does not have any metamorphic soil. We could not find any metamorphic soil in comparison to the Samail Ophiolite. The Ophiolite is considered to be an uplifted chunk of Indian oceanic crust. And paleomagnetic constraint point to nature spreading direction that was roughly north-south during late Jurassic to early Cretaceous. Now, the Cretaceous-Paleogene transition before 65 million years, indirect conversion among India and Afro-Arabia brought about fragments of the early Indian Ocean to be thrusted into the basin, into the Batain Basin in eastern Oman. I made several argon, and uranium-lead age dating, and we found that the magma span an age between 83 to 145 million years. If we compare it to Samail, the magma span only 94 to 96 million years. That means 2 million years. And here we have around 60 to 70 million years of magmatism, active magmatism. Now, if we analyze the rock and ore bodies found within the Masirah, all magmatic rock and ore bodies, they gave us a MOR composition by using analysis of spinel, chromite, or by using analysis of pyroxene, olivine in the rock, as well as in the chromite, they give us a MOR composition. And even if we plot this famous diagram, we'll find that the Masirah rock are lying along the MOR ocean island basalt array. And here, by comparing the chondrite composition, we'll find that the Masirah magmatic rock are lying or very comparative with the Indian Ocean composition. So before 260 million years, Masirah was not there. Here we have India, Antarctica, Australia, and Seychelles. And here we have Madagascar, and this is Arabia. Now, if we come around 150 million years, the Masirah Ophiolite, this is Masirah Ophiolite, a small m, it was formed along an east-west trending edges, as you can see these ridges, at latitude of 40 degrees, when Madagascar and East India broke away from Arabia and drifted southward. Now, the opening of the North Somalia basin began with before 150 million years, and that caused the division of Madagascar and Seychelles in India block from the Afro-Arabia, and the Helmand block moved northward. If we go to the age between 130 million to 118, we'll find that before 118 million years, these sinistral fault between Madagascar and Seychelles started. And these structures may extend along the eastern edge of Oman in response of India's rapid northward movement. So we start having these sinistral fault before 180 million years. Now, at 75 million years to 65 million years, we have the ocean accretion between Madagascar and Seychelles, and India block began, which began 86 million years here, this story here. And then we have ocean creation between Seychelles and India began at 65 million years. And there was a possible collision between India and Karman block. And this collision caused the Masirah Ophiolite obduction in the Maastrichtian to Paleocene ages. So the collision now between India and Eurasia began 35 million years. India and Eurasia started to collide at this age before 53 million years. And this is the present situation, actually, for 65 million years. This is Masirah, and this is Samail Ophiolite, and this is the Owen ridge here. And here we have the different Ophiolite related to subduction zone in Muslim Bag, Bila, and all these Ophiolite are related to subduction zone environment, while the Masirah is related to typical mid-ocean ridge environment. And before 20 years, actually, French group started to do some geophysical profile across the Ophiolite in order to give a real better situation. And actually, they failed to give good result for the Ophiolite in the Gulf of Oman. This is the result. And mostly they got ambient noise preliminary result due to receiver function, surface wave anisotropy, etc. So there's a need actually to redo these experiments with the new equipment and a new study, especially to study the profile of the Ophiolite remaining in the Gulf of Oman as well as in the Makran area. Now, an interesting new theories about the Samail Ophiolite was proposed by one geologist, remote sensing man from United States. He proposed an impacted crater origin for the Samail Ophiolite, depending on the crescent shape. He just showed the crescent shape of this Ophiolite here and the other side. And he suggested that it could be formed not by supra-subduction zone, not mid-ocean ridge, but it could be remain over impacted crater, and suggested that the diameter of this impacted crater is 500 kilometer, which is enough to give a transient diameter 250 and excavation depth to 25 kilometer. And this 25 kilometer is enough to dredge mantle sequence and crustal sequence in Oman. And he compared it with other impacted crater which brought ultramafic rock and other which did not provide mantle section due to the excavation depth. So when the excavation depth is more than 15 kilometer, it brings ultramafic mantle sequence plus crustal sequence. And he compared it with the famous Chicxulub crater, which has a diameter of 200 kilometer. The excavation was 10 kilometers, so it did not brought any ultramafic rock or mantle sequence to the continent. So this is the way he described it. This is the crescent shape of the Samail Ophiolite in comparison with the Ophiolite and the Iran side. Of course, he have only clues from remote sensing, and this could be actually proven by taking some seismic study or some geophysical study to prove it or disprove it. But anyway, we have several melange here, several breccia, which could indicate that there must be something happening. At the end, I'd like to thank all groups who work in Oman. Special thanks to Adolf Nicholas, who passed away last year, Bob Coleman, and Chirek Peters, who contributed a lot in their study to the Ophiolite of Oman. And special thank also to Francois Bordier from France. All of them, they contributed a lot to the Ophiolite of Oman. Now, through literature review and different study, actually, I collected around 35 questions need answer. And the debate continues because several questions could not be answered from the previous study. So I'm not going to go through them, all of them. You can have a look at them and do your own research to give answer for these questions. As example, how thick was the Samail Ophiolite mantle section during abduction, but before later deformation and see that. How can we reconstruct the structural thickness of the Samail Ophiolite if it is less than 20 kilometers now? With the pressure depth condition recorded by the metamorphic soil, the depth should be more than 70 kilometers actually for the metamorphic soil. How come that the Samail Ophiolite thickness is less than 20, it's just 15, etc. So we have many questions can go through, and it's still, the debate is still going on. And thank you very much.